So in the third part of this KSP video, I want to spend a little bit of time talking about figuring out when you mix solutions. So to do precipitation reactions, will you or won't you see a precipitate? You've all faced situations where you mix two solutions together and your prediction was you do see a precipitate, but when you do it, you actually don't. So why is that? And I've told some of you that, well, you just didn't have enough product created. You didn't use enough drops, that if you had enough product, you'd actually see something. So this question, or this problem, is going to let us address, will we or won't we see a precipitate? All right, so here's the situation we're going to be faced with. So if you've got 10 milliliters of a 0.02 molar solution of lead nitrate. You've got 30 mils of a 0.030 molar potassium chromate. Will we get a precipitate? So you think about the double replacement reaction. The precipitate that we're predicting we should get is lead chromate. But we are not going to see solid lead chromate form until we establish that equilibrium, until we have enough ions in there so that they are attracted to each other and will start precipitating out a solution. So at what point do we need to have that? That's where the idea of KSP comes in. So like I said, we take these two solutions, they're separate, but when we mix them together, what happens? We get the precipitate forming. So how do we deal with that? So step one, are we going to form, is a sparingly soluble salt formed? So we look at solubility rules and we predict, well, we should get lead chromate, but again, that depends on solubility. So lead chromate is the thing that we're worried about. So that's going to be our focus. Lead chromate is the sparingly soluble salt. So we need to focus on its KSP in order to decide whether we will or we won't. Okay. The ion concentrations that we have to work with are those that we started with from the lead nitrate solution and the potassium chromate solution. And we also know by looking it up that the KSP for lead chromate is 2 × 10⁻16. So if a precipitate forms, that means we have enough ions here to drive the reaction back to the left to create solid. So we have to have enough ions in order to drive it back that way. That means this combination of ion concentration has to be greater than this number here. So let's see how we figure that out. Okay, like I said, that'll happen if Q, the numbers that we actually have to work with, is greater than the 2 × 10⁻16. Okay, so we're going to find the concentrations. Now you got to remember, we started off with a certain concentration of lead nitrate and a certain concentration of potassium chromate, but we diluted it. So to get the final concentration of the lead and the chromate ions, we have to do a dilution calculation. So for the lead, we started off with 15 mils of 0.024 molar, but we mixed it with 30 milliliters of the other solution, so a total of 45 mils. That means the lead ion concentration is 0.008, and that means that the chromate ion concentration is 0.020. So those are our equilibrium concentrations of the two ions. So if you think about the ice chart we would have to set up, actually you don't even really need to, because these are our given concentrations, but these are these are the not the plus, not the change, but these are the E concentrations, these values. So what do? We multiply them together because we don't have to square anything. They're 1-to-1 ratio. We get 1.6 × 10⁻⁴. So we're going to compare. KSP is 2 × 10⁻16. Q is 1.6 × 10⁻⁴. This number is much larger than this number, so yep, we are going to see a precipitate form. So keep those steps in mind. And actually, we're going to quit here and take a look at other factors affecting solubility later. I want to give you guys a chance to get these basic KSP things down first. So you've got plenty of problem sets over the next few days that you're going to work on.